out and did it in a strange way. Okay. All right, so are there any questions about where we were? And actually, out of curiosity, just to get a quick temperature check, how many people have done this kind of ODEs and PDEs before? Sorry, this kind of specifically sort of systems of first order linear ODEs before? And if you haven't, you shouldn't feel embarrassed. That's why we're covering all the math here. Okay, so 1, 2, 3. Okay, so a decent number of you. Yeah, about half. Seems about right. So yeah, so if you haven't done this stuff before, if you haven't done this stuff before, so don't worry too much. We'll go through it carefully. But it's the big technique that we're going to be using, you know, from kind of this lecture on through the next few is linear algebra. So this is definitely where if you need to, I would really recommend going and brushing up on your linear algebra. So we should have that. Okay. Y'all can see this. Okay. All right. So because basically the whole game here, and we already saw this at the end of the last lecture, is going to be eigenvalues and eigenvectors. And we're going to spend a lot of today going through sort of these simple first order systems that look like, so what are we going to do today? Is we're going to try to really fully understand first order systems of linear equations of the form first order say what are these technically? First order linear constant coefficient systems. First order homogeneous linear systems with constant coefficients. And what is that? These are things of the form dx dt, which again is some vector x1 prime up to xn prime is equal to ax, where A is a matrix with constant coefficients. You can't see anything. Can other people see? Oh, no, I can't see anything either. Let's, thank you for letting me know. Okay. Okay, yeah, thank you for, let me fix that here. What went wrong? Sorry, I think you can either share your entire screen or you can share a window. And so I thought if I shared the window for OneNote, then when I went full screen, it would actually show me everything. And apparently that does not happen. Okay, cool. Thank you guys for letting me know. Okay, so this is what we're trying to understand. We're going to really fully understand first order homogeneous linear systems with constant coefficients. And the technique that we're going to use here, and so these are simple things, right? So these are So our sort of like example, our sort of standard example that we're going to pound on really hard in this lecture and try to really understand. Example is something of the form, so x1 prime equals a1 x1 plus a12 x2, a2 prime equals a21 x1 a22 x2. You still can't see. Oh. That's weird. All right, well, okay. Try to get that sorted out. Well, maybe we'll just live in this here. Okay, that looks promising. Okay, thank you. Sorry for the technical difficulties here. Okay, so basically this is going to be our standard example. And here, so x vector is x1, x2. X prime vector is going to be dx dt for us. So for the next few lectures, probably for most of the rest of the class, our dependent variable is always going to be t. X prime 2 and a is just the constant, or the matrix of coefficients. Okay. So at the end of the class last time, actually, let me say it. Jump into that. So the reason that we want to understand this example so well is it turns out that this example basically tells us everything that we need to know about much more general families of equations. So if we can really understand the 2x2 example and really understand everything that's going on with it, that actually basically tells us everything about all of the higher order examples. There's like a couple of boundary cases that I won't talk about. I'll mention where they are, but like if you have some sort of weird weird doubling of eigenvalues and stuff like that, if you don't have certain eigenvectors. But in general, understanding this 2x2 example is going to tell us everything about the n by n example. So understanding 2x2 example in this case is really helpful. Everything. Higher end examples. In addition, so these 2x2 systems are really simple, but they actually do still show up. We kind of saw where they were going to come from, these salt tank models and lake pollution models, but they actually show up quite a bit in biokinetic modeling. So, and we'll show how that happens later today. But basically, when you're trying to understand things like drug transport through the body and molecular transport through the human body, you really can set it up as sort of a salt tank model. And it turns out like a lot of the dynamics, whether or not it's sort of concentration flow or flow across a semi-permeable or a permeable membrane, wind up coming out in terms of these linear equations. So these things are interesting in their own right. But sort of even more interesting, and this is what we're going to see on Wednesday and then next week, is that these are going to form the equilibrium solutions. Essentially, they're going to form the equilibrium solutions for much more complicated nonlinear systems. So basically, if we want to understand, so if you remember, before we had our equilibrium solutions, and they were kind of, for autonomous equations, there were these lines, and they sort of weren't interesting, they were the constant solutions. But what they told us was they gave us all of the information about the behavior of all of the solutions around them. The same thing is going to happen here. So for these much more complicated systems of nonlinear differential equations, the solutions we're going to be able to cash out, sorry, the equilibrium solutions we're going to be able to cash out exactly in terms of these equations, these kinds of very simple systems of differential equations. And in addition to that, it's going to tell us a huge amount of information about the local behavior of the solutions. So we're going to start by really understanding this 2x2 example. That's going to tell us sort of everything about higher order examples, but it's also going to tell us everything about the equilibrium behavior of nonlinear autonomous equations. Also, these systems a lot about the equilibrium solutions to systems of nonlinear equations. Okay, any questions? Okay, so where were we last time? So at the end of the discussion last time, we had written down the following formula. So let x prime equals a x as of. And let's assume that A has a basis of eigenvectors. I'm not sure I answered blown away. Basis of eigenvectors, v1 up to vn, with corresponding eigenvalues lambda 1 up to lambda n. Then the solution, or the general solution, I should say, is going to be x vector equals C1 e to the lambda 1 t times v1 plus up to Cn e to the lambda n t times Vn. Okay. So before we say more about this, and I do want to say at least one more thing about why this is kind of the right solution, or another way that you could see that. Let's just do an example. So if you've done this before, race me to the solution. Let's say that we have x1 prime equals minus 4x1 plus x2, and x2 prime equals 4x1 minus 4x2. Okay, so this is a perfectly good linear system of linear equations. And if you remember, the way that we kind of thought about this was we'll say, well, we'll make a coordinate transformation that will diagonalize the system, then we'll solve it, and we'll make the coordinate transformation back. But of course, we've got the general formula for that. So we can just sort of crank through the pieces. So how do we solve? And let me. So first, A is equal to, well, write this down as matrix. So this is minus 4, 1, 4, minus 4. So we find the eigenvalues. The determinant of A minus lambda times the identity matrix. So determinant is sometimes denoted by just line brackets. So this is minus 4 minus lambda, 1, 4, minus 4, minus lambda. What are we going to get here? So this is going to be 4 plus lambda squared, right? Determinant is B times A minus, sorry, A11 times A22 minus A21 minus A12. So minus 4. I'm not demonstrating particularly good lining up of my equal signs, but we'll, hopefully we can let that pass. Lambda squared plus 8 lambda plus 12, and of course we can factor this then as lambda plus 6, lambda plus 2. And so we have two solutions. Oops. Two solutions to the eigenvalue equation. Lambda equals minus 2. 6. Oh, and I'm sorry, I should pause this for a second because I realized, let me just give a quick refresher as to how you find eigenvalues and eigenvectors. So we're just going to move this down a little bit. say. Okay, so this whole thing is in terms of eigenvalues and eigenvectors, so let's remind ourselves how we find them. So finding eigenvalues. So we do it first we find eigenvalues, then we find eigenvectors, right? And so an eigenvector V, a matrix. I'm just going to go with matrix, of course, also linear transform A. Eigenvalue lambda. Is any vector such that A times V is equal to lambda times V. Okay. So how do we find these guys? Well, if we want this equation to hold, above as A times V minus lambda times V. We can factor a V out now, but we have to be a little bit careful, right? So this is going to be A minus lambda times V, but of course, to have this matrix subtraction work correctly, we have to multiply this by the identity matrix. And in a certain sense, we can secretly be doing that here as well, right? Like lambda times the identity matrix times V is just lambda times V. So this is a perfectly fine thing to do, and it makes the addition work out, right? We can't actually, mathematically, we can't add, we can't add matrices of incompatible dimensions without defining how. Okay, great. So we want to find, lambda such that this is true. Just move this again really fast. We want to find lambda such that this is true. And we know, okay, we want to find lambda such that this is true. And but what this is asking us for, right? So this is equal to 0. And this is a vector equation. Oh, and I said I'd always have my little vectors. Let me do that. So this is happening as a vector equation, right? And so what this actually means is that this matrix is degenerate, right? It has some non-zero, there's a non-zero vector such that when we multiply that vector by the matrix, we get 0. In a linear transform sense, there's a non-zero vector which is transformed to the 0 vector, which is collapsed down. So what does this mean? This means A minus lambda I is degenerate. And so in particular, matrices are degenerate if and only if the determinant of A minus I is equal to 0. Great, so we just need to find lambda. a lambda such that this equation and then actually finding the vectors is, well, given such lambda, we just solve the equation up here. So given such lambda, we solve a minus lambda I times v equals 0 for v using, row reduction, Gaussian elimination, whatever your favorite technique is. Okay, so any questions before we jump into the example? So this is just your quick reminder of how this is going to work. Okay, so let's go to our example. So in our first step here, again, we're going to be finding our eigenvalues. And we do exactly what we said above. So we're trying to find the values of lambda such that this matrix becomes degenerate, because if it's degenerate, then there is a zero solution, and so A has an eigenvalue solution. And we get that lambda needs to be equal to -2 or -6. Are there any questions as well about this computation, or does this make sense to everybody? Okay. All right, so two solutions to the eigenvalue equation. So let's find the eigenvectors. Okay, so and again, you can kind of do this in whatever your favorite way is. Here's the way that I was taught in linear algebra, 10,000 years ago. So what do we do? So we'll let lambda 1 be -2, then a minus lambda 1I is going to be what? -2, so -2 plus 2 minus 2, 1, 4, -2. And then to do this the slow way, of course. So then we can solve this. The augmented system. So for the 2x2 example, you can probably just look at that and tell me exactly what the answer is. But to just do it out slowly once, the augmented system, so we've got -2, 1, 4, -2. We put the target on the right-hand side. In this case, the target is 0, 0. We want to find a vector such that when we multiply it by this matrix, we get 0, 0. And then we just use our standard Gaussian elimination. So 2, 1, multiply this by 2, add it to the next line, we get 0, 0, unsurprisingly, great, okay. And so then what is the vector such that if we multiply it by this, we get 0, 0. We're going to get v1 is equal to 1, 2. Great. So I can do another step here if people don't remember this, but are we good so far? Okay. Are you still with me? Just want to make sure because there's nothing. I want to make sure I haven't lost everybody. Okay, fabulous. Okay, maybe just a quick question. Speed-wise, are people following, or is this, is this kind of like, yes, move on, we got this, or am I going too fast for anyone? Okay. Is that that's a no, I'm not going too fast, I assume. Cool. Do you tell me to slow down or speed up if you need me to? But I may not speed up that much because I want to make sure that if anyone is a little bit behind, that they will get what they need, even if they don't want to speak up. So, okay, great. So this is eigenvector 1. Let's look at 2. So for lambda 2 equals -6. And take a second, erase me, what do we get? So a minus lambda 2I is going to be equal to -4. So 2, 1, 4, 2, blah, blah, augmented system, 0, 0. This is going to immediately give us, immediately going to give us 2, 1, 0, 0. What does that tell us? It means that the first element, v1, has to be, so 2 times v1 plus v2 is equal to 0. So v2 is going to be equal to 1 minus 2. Or alternatively, any multiple of this, right? So if v is an eigenvector with eigenvalue lambda, then of course any multiple of v is as well. All right. So to summarize, we have lambda 1 equals -2, lambda 2 equals -6, v1 equals 1, 2, v2 equals 1, -2. Yeah. So let me just do it once out in its full glory, because I'm kind of in some sense skipping the most important step. So let v2 equal, call it y1, y2. So then basically what we have here, right? So we have yeah, and thank you for asking. All independent and then get the dependent from the last equation. Yeah, no worries. So what we want here is a minus lambda 2 I v2 equals 0. So the other way to say this, right, is that we want to solve 2y1 plus y2 equals 0. This is secretly 0 vector, or y1 plus 2y2 equals 0. And there's different ways that people have been taught to do this. The way that, you know, they're basically all computationally equivalent. The way that that I was taught to do it, and I think that they're still teaching this, at least in some places in the US, is through an augmented system. So what we do is we take this system here and we just write it as big matrix with the equality sign coming in as a line. So we've got 2, 1, 4, 2 is equal to 0, 0. And then we just do all of our steps like you would do. So, you know, okay, so we're going to subtract 2 times the first line off the second line, right? Just do it all in the augmented matrix. So basically, it's just to not have to write y a bunch of times. But so we subtract 2 times the first line off the second line. Great, 0, 0, 0, 0. And if these were not 0 and 0, if they were 1 and 4, then we would do the same thing on the other side. And then we sort of rewrite this as an equation, and what are we left with, right? So this is going to imply that 2 times y1 plus y2 is equal to 0, or y2 is equal to 2 times y1. And and that's actually as far as we're going to get, right? Because if our assumption is that when we multiply v times the matrix, we get 0, then that'll also be true for any multiple of v. So for 10 times v, for 100 times v, we'll still get 0. So we're going to have 1 degree of freedom. So setting y1 equal to 1, we get, sorry, that v2 is equal to 1, 2. And so that's kind of that's the more expanded way to do it. And I apologize because when you do enough of these, you can kind of look at the first equation and say, well, okay, so I just need to figure out the thing that I multiply by, or that I take the dot product with 2, 1 and get 0. And, oh man, I'm sorry. There should be a minus sign there. Yes, exactly, thank you. Okay, so yeah, and thank you for asking, because again, if you have a question, I can guarantee you that half the class has it. So, especially if you want me to just go through something in a few more steps. I occasionally skip steps in places that it's not obvious, just because. But so yeah, thank you. Okay, so in psi, I think we get values 1, 1, 1 to all independent and get the dependent from one equation. Could you say something? Could you say another word about that, psi? I'm not quite sure what you mean by that. Oh, I see. Thank you very much. Cool. Okay, so here we go. So we've got maybe your last step. Y1 equals 1. Oh, yeah, so why did I pick y1 equals 1? Yeah, so basically, I could have actually picked y1 equals anything but 0, right? And so let's just go through and check this really fast, because it's worth seeing again. Right, so let's actually then, so let's go through here and undo this. So A times V2, right? What are we going to get? So A is, myself, minus 4, 1, 4, minus 4, 1, 4, minus 4 times 1 minus 2. And this is going to be, what, minus 4 minus 2, minus 2, and 4 plus 8, which is minus 6, 12, which indeed is minus 6 times 1 minus 2 as claimed, right? But watch. So let's say that I picked something else for y1, right? So that's essentially going to be equivalent to just multiplying the whole thing through by a different number. So let me say as an alternative here, what if I picked y1 equals, I don't know, what's your favorite number? Well, no, I shouldn't say that. Someone's going to pick like 10 million or something. Let's say we picked y1 equals minus 2. So then v2 is going to be minus 2, 4, and a times v2 is going to be minus 4, 1, 4, minus 4 times minus 2, 4. And a little bit of work, that's going to be 8 plus 4, 12. And that's going to be minus 8 minus 16 is minus 24, which again is going to be equal to minus 6 times minus 2, 4. Okay, so what this is telling us, right, is that actually I can pick A to be anything I want, and I'm still going, so I can pick y1 to be anything I want, and I'm still going to get an eigenvector, right? But in particular, you can also see that these guys are just a multiple of each other, right? So v2 is, so let me call this v2 prime. So v2 prime is just minus 2 times v2. And that actually makes the fact that this works a lot clearer, right? So change colors of things. That's cool. So here, v2 prime is just minus 2 times v2. So actually, we can just use the properties here, right? Because in fact, we have a v2 prime is equal to a times minus 2 v2 by commutativity of scalar multiplication. This is minus 2 times a v2, or minus 2 times minus 6 v2. We're combining this minus 6 times v2 prime. So indeed, any scalar multiple of an eigenvector is also an eigenvector. And this is more clear to understand from the linear transformation perspective because eigenvalues, the eigenvectors are non-transformed directions. But so it becomes clear here that we've made a choice somehow, right? So if we make a choice, then if we have to make a choice, then how do we make that choice? And the answer is going to be, keep moving this down. The answer is going to be that the choice that we make gets absorbed into the overall constant of integration. So it's actually not going to matter. You can make whatever choice is most convenient for the calculation. So the choice is absorbed C later. So pick the easiest one. Any questions? Okay, so here we go. And it's good to ask questions about this because essentially this is like all the work, right? So by our formula, so by x bar equals C1 e to the lambda 1 t v1 plus C2 e to the lambda 2 t v2 we have as a vector equation x1 x2 equals C1 times e to the lambda 1, great, minus 2t times v1, 1, 2, plus C2 e to the minus 6t times v2. And as a vector equation, right, this is actually just two equations, right? This is just x1 equals C1 e to the minus 2t times 1, technically, plus C2 e to the minus 6t times 1, technically, and x2 equals, say, 2c1 e to the minus 2t minus 2c2 e to the minus 6t. Okay. Any questions? So this is it. And so we can solve these equations like completely as long as we know the eigenvalues and the eigenvectors. And what's the behavior here? So we have a whole two-parameter family of solutions here, right? It's a family of solutions that depends on two real parameters, and C1 and C2 can take on any two real numbers. So what is the asymptotic behavior? What happens to these are, so these guys are functions. What happens to this pair of quantities x1 and x2 as t goes to infinity? Isn't v2 2, 1? Did I get these backwards? I think so. Let's see that. No, if our check above, I mean, did I do something terribly wrong? Because if our check above works, then it should definitely be 1, 2, or sorry, 1 minus 2 or minus 1, 2. Yeah, I think we can go through and we can check. So we multiply 2, 1 by a, we're going to get 7, so we're going to get minus 7, 4, which isn't going to be an eigenvalue. So I think that this is correct, but do always check me. What do we think? So what is the asymptotic behavior? So say it another way, when t goes to infinity, where does x1 of t, x2 of t, anyone? Exactly. It'll approach 0, 0. So the limit as t goes to, wow, x1, x2, 0, 0, right? And this is just exactly because what is this? This is the sum of exponentials, okay? And the coefficient of the exponential is negative. And so in some sense, we can actually see that, like, this is really straightforward. This is both lambda 1 and lambda 2 are less than 0. So that's actually another nice thing about this, right? If all we wanted to know was the asymptotics of the system of equations, if all we wanted to know was whether or not the solutions approached 0, we could have stopped here, right? We could have computed the eigenvalues and said, oh, they're both negative. Well, okay, so I know exactly what the asymptotics of this system of equations are. And that's it. Go home. Of course, we want to understand what happens a little more fully than that. But in this case, because again, since the eigenvalues are going to exactly govern the exponential behavior, their sign is going to exactly give us whether or not the system of equations goes to 0, goes to infinity, whatever happens. And so there's a picture that we draw here. Called solution space. And the picture is if we have x1 and x2, and if we think about some point here that is, for instance, x1 of 0, x2 of 0, what happens to the solution? Well, roughly it's going to fall in to 0. And pretty directly, right? Because so we would have to figure out what exactly C1 and C2 were to make these coefficients to work out to be what exactly this is. But sort of no matter where it starts, these solutions are all going to fall in to 0. And do it quite rapidly, do it exponentially. Any questions? Okay. So there's actually a slightly more precise picture we can draw. And that's to remember that the actual form of this, so the form of this guy makes more sense, actually. We really do want to think about this in its vector form. So now we're going to have C1 e to the minus 2 lambda, times t, minus 2t times v1, so 1, 2, plus c2 e to the minus 6t times 1 minus 2. And let's actually draw these vectors. This is a rough sketch. Let's draw a slightly less rough sketch. X1, X2. So we have the eigenvalues, right? So we go one in the X direction. So this is roughly going to be V1. So in fact, we have a line in the direction of V1. Again, that we said that it doesn't actually matter how we scale V1. It's still going to be an eigenvector. Similarly, we're going to have a line in the direction of V2. And we can ask what happens along these eigenvectors, right? So in particular, if C1 is equal to 0, then we're at a point somewhere along this line. So here, this is C1 equals 0. Oops, other way around. Sorry, this really wants me to pay attention to it. Sorry, if C2 equals 0, then we're somewhere along, then our initial condition is going to be somewhere along this vector, and in fact, it will stay there and go into 0. And similarly, if C1 equals 0, then we're starting somewhere along the C2 vector, and we follow it straight into 0. And if we start someplace else, right, we can think of this as some combination. So if we start here, we can think of this as some linear combination. Actually, take that back. Do it in this color. So this is basically, sorry, C2 times V2, C1 times V1, and this point here is going to be C1 times V1 plus C2 times V2. And then what happens to it is that you can see what's going to happen is that both of these vectors are going to contract at a different rate. So both coefficients will contract at rate. Sorry, I should say will contract with e to the lambda 1 t and e to the lambda 2t. Actually, there's no reason to be precious about this. We know what lambda 1 and lambda 2 are. E to the minus 2t and e to the minus 6t. Respectively. So basically, how is this going to go to 0? Well, it's going to kind of shrink in this way. As we contract these two things down. And of course, we're going to contract C2 much faster, actually, than we're going to contract C1. So this may be, this actually may be incorrect. It may be more like that. Okay. So we're going to do a couple more examples, but are there any questions before we move on? So at least here, all the pieces are represented. And understanding this picture and the other pictures we're going to draw are kind of important because, again, these things are going to give the geometry of our solution space to more complicated nonlinear equations shortly. Why did you change the direction of the bow? Yeah, so I should be clear that I'm kind of guessing here, but the reason basically, right, is that so how do we get to 0? And we'll see maybe a more clear example in a second. This is a very good question because I can brush over it, but we get to 0. We get from this point here to 0 by contracting the vector along v1 and contracting the vector along v2. But we don't do that at the same speed, right? The coefficient, we contract the vector along v1 at a rate of e to the minus 2e. And we contract along v2 at a rate of e to the minus 6e. So basically, we're going to be contracting along we're going to be contracting the v2 direction significantly faster than we're going to be contracting the v1 direction. And so that would seem to imply that we have a lower bow as opposed to the upper bow, which would seem to imply that we're contracting v1 faster than we're contracting v2. That you should really just check it, basically. You know, there's a little bit of intuition for that kind of based on what I just gave you, but you should really think of this analysis is most helpful as like an asymptotic analysis. It's a little bit hard to figure out for some like random point what exactly is gonna happen. So that would be, yeah, but that's the reason that I changed the picture there. Any other questions? Okay, so let's do another example. And so those of you for whom this is old hat, I would say again, race me. Yeah. Oh, let me see what this is called. So this is called if all solutions fall into, so if lambda 1 and lambda 2 are less than 0, all the solutions are asymptotic to the origin. And we call the origin a stable node. Okay, so what if we have, let's go through this again, x1 prime x2 prime is 2x1 plus 2x2 5x1 minus x2. Okay, so we just need to determine the eigenvalues and the eigenvectors. And I'll go through this, but I'd say you should race me and see if you can get there faster. So here, what we have A is going to be the matrix 2, 2, 5, minus 1. So the eigenvalues are going to be determinant A minus lambda I, which is 2 minus lambda, 2, 5, minus 1, minus lambda. Oops. Vertical bar. And so we're going to get 2 minus lambda minus 10. And that is lambda squared minus 2 minus 10. Let's do it at 1, so minus 12. Which we factor to be plus 3 minus 4. So let's call lambda 1 minus 3 and lambda 2. 4 just to keep, I probably should have done this before, but to keep sort of increasing the eigenvalues with the numbers. Okay, so eigenvectors. So for lambda 1 equals minus 3, we're going to wind up with the augmented system 5, 2, 5, 2, 0, 0, which pretty quickly implies 0, 0, 0, 0. So 5 times y1 plus 2 times y2 equals 0. So the simplest way to show this to me is just, what do we do? Well, we'll do 2, 5, and make one of them negative. Great. Similarly, lambda 2 is going to be equal to 4. We have the augmented system then, so subtracting that off, minus 2, 2, 5, minus 5, 0, 0, minus 2, 2, 0, 0, 0, and what are we going to get? So, minus 2y1 plus 2y2 equals 0, or v2 equals 1. Great. Okay. So hopefully we all agree. Quick question. So at this point, you will probably have noticed a trick with 2x2 systems where we really don't need to write down this first step, because with a 2x2 system, when we're finding eigenvalues, if we've done everything correctly, the absolute first thing that's going to happen is that by solving this, we're just going to get rid of the second step, right? That has to happen if we have a degenerate matrix. I would still highly encourage you to do it, right? It's very, very tempting to just write down the first step and then jump straight to the vector. I'd highly encourage you to, at the very least, write down the whole augmented matrix, because it is an error check. One of the big places the errors will come out of this is that you do something incorrect. If you do something incorrect, if you, for instance, solve the eigenvalue equation wrong or just forget something, if you write down the whole augmented matrix, you'll immediately see that you can't solve it. And so then you can save yourself. It's very easy to not notice that if you try to take a shortcut. So I would highly recommend actually writing down the whole augmented matrix. Okay, are there any questions about this computation? Okay, so questions about this computation aside, what we, like, again, the computation is great. It gives us an exact solution, right? Let's write it down. So x equals C1 e to the minus 3t times 2 minus 5 plus C2 e to the 4t plus 1, 1. So it gives us an explicit solution. So if we have initial conditions, we could, of course, solve them for C1, C2, and then actually get something. But it tells us a lot more than that, right? We want to understand this whole family of solutions, right? We don't just want to understand a single one. And so here's a question. What are the asymptotics of this family of solutions? What are forward asymptotics? Just maybe say it more simply. What happens as we take t to infinity? What do you think? Right, so, well, yeah, so kind of, right? So it's like one part of it approaches infinity, while the other part of it approaches 0. So we sort of shrink the dependence on this eigenvalue and inflate the dependence on this one. So shrink. And inflate. And so actually, of course, what this will wind up with is something that's 0 plus something that's very, very large. Writing it out in equations is a little bit more clear, right? So we have x1 equals c1 e to the minus 3t, I'm sorry, 2, plus c2 e to the 4t. Well, this is clearly going to go to infinity as t goes to infinity. Oh, I should say, sorry, this will go to plus or minus infinity depending on the sign of c, of course. Sign of C2. And x2, we're going to get minus 5 C1 e to the minus 3t plus C2 e to the 4t, which is also going to go to plus or minus infinity. Same as I said up there, right? guy as Jolly pointed out, is going to go to 0. But something kind of interesting happens as well. So yes, it is true that both of these go to infinity, right? But they both sort of go to infinity together. In fact, if you look here, in this specific example, they both go to infinity at exactly the same rate, right? Basically, for large t, so for large t, so large but finite, we actually are going to have that x of t is equal to, is not equal to, is approximately equal to c2 times e to the 4t, c2, e to the 4t, right? Because the whole first components will have vanished. So this not only does this go to infinity, it goes to infinity along the eigenvector v2. Let me draw a picture and show you what I mean by that. So here we have our equation. We've got v1, v2. So v1 is 2 minus 5. Let's just say it's roughly this. So v1, we've got, in fact, we should think of this as a linear subspace because, of course, it could be plus or minus. And then v2, well, we have another linear subspace. And so let's say that we have a point here, right? Oh, maybe let's say that we have a point here. So if this is going to be C1, V1, and this is C2, V2, then just like before, what's going to happen is that, for x of t equals C1, V1 times e to the, minus 3t plus C2, V2, e to the 4t. As t goes to infinity, of course, now, so V1 is going to shrink down to 0, but V2 is going to grow. And so what we're going to get is a trajectory that sort of looks like, you can kind of imagine these shrinking and growing at the same time. This is going to be a little bit inexact, but it's going to roughly look like this. And we can imagine other things, other points in here that are going to do the same kind of thing. And in fact, if we had other trajectories on this side, again, the V1 would shrink, V2 would grow. On the other side of V2, we're going to get it happening the other way. So the solutions are sort of asymptotic to infinity, but they're more than that, right? They're not just asymptotic to infinity, they're also asymptotic to the eigenvector v1, v2, or they're asymptotic along, they're asymptotic along the eigenvector v2. So solutions sort of go to infinity, but along V2. So this is called a saddle. Or a semi-stable node. Actually, okay. Are there any questions about this picture? And or how we got to this picture? Okay, so let's start to think about what will happen in higher dimensions here. Question. If we have a 3 function system, so x bar equals ax, where lambda 1 equals -3, lambda 2 equals 2, and lambda 3 equals 7. With eigen vectors v1, v2, v3. What is the asymptotic behavior going to be? Any guesses? And I'd say even if you don't quite have an answer, take a crack at a guess. We can do, and we'll discuss a little bit about what should happen here. Or if you do know the answer, feel free to just say it. Okay, yeah, so we have parse. Okay, so everything that people are saying in the chat here is correct, I think, under interpretation. So, okay, so it will certainly be the case that everything's going to go to infinity on some level, right? Like, they'll at least will not go to 0. It'll be something unbounded. Could be plus or minus infinity. it will, and what everyone's observing is correct, that, so we're going to get x is, our C1 e to lambda 1. We actually be precise here. T 1 plus C2 e to the 2t. V2 plus C3 e to the 7t V3. And absolutely, so we're going to have two of these guys are going to be expanding directions, and two are going to be contracting directions. Sorry, one's going to be contracting direction. So this is going to go to 0, and this is going to go to infinity, and this is going to go to infinity. And what's going to happen if you think about it, right, is that this guy's actually going to go to infinity much faster than this, right? So this goes to infinity the fastest. And so eventually, so we will, of course, so the first thing that's going to happen is that one of these is going to contract out. And then we're going to have a competition between these two exponentials. So this goes to infinity slower. But what is eventually going to happen, right, and it could take a very, very long time, especially given what C2 and C3 are, what will eventually happen is that this guy is going to dominate. And for very large t, x is going to be approximately C3 e to the 7t V3. It's a little counterintuitive, right? Like, because you would sort of think that the exponential, the exponential behavior here is, they're both exponential, they're both increasing, it's going to be some combination of the two. But in some ways, it kind of makes it easier because it means that, if you're in the semi-stable case, everything eventually does asymptote the same to whatever the largest vector is. You could have more complicated behavior if it turned out the two of the eigenvalues were actually the same, right? And that's entirely possible. We're not really discussing that case so much. But if you had two of the eigenvalues be the same, then you could wind up with some more complicated behavior. But that's not generic. Okay, any questions? Question? What is the last case, right? So we have two cases. So what is the final, well, the final case, but I guess we sort of discussed it. So we want to ask this question. I'll just propose it. So finally, if we happen to have lambda 1 and lambda 2, and let's order them. It's just going to make life easier. Greater than 0. Then we call this an unstable node. Unstable node. And the picture is roughly going to be, if this is some V1, this is some V2, then, well, things are expanding out. That's the best way. They will eventually become asymptotic to the larger one. All solutions go to infinity along the eigenvalue corresponding to the largest, eigenvector corresponding to the largest eigenvalue. Okay, any questions? Okay, so let's take a few minute break here. So there is, of course, one more case, or one other whole set of cases that we're going to talk about when we get back, that expand the behavior to be quite a bit more interesting. So we're already getting sort of interesting behavior. We'll see that we can get a lot more interesting behavior in just a second. So so it is 2:35 my time. Let's return at 2:45 and call it a day. And then we will zip through, talk about complex solutions, and that should get us through to the end of class. All right. So I will be back in just a minute. Are there any quick questions before I jump off for a second? All right. Great. So to say, one of you did a very nice SymPy slope field for the first homework. And there's, I'll try to incorporate that into something. Yeah, if you want to play around with this, and I would definitely recommend taking a look at some of the stuff out there. I think the Bluffton slope field plotter is the best one I'm taking a look at. And just yeah. To give like a kind of quick example, you can get some nice examples of like what we've done here. Play around with them a little bit. We'll also. Whoa. So if you want to take a look at like what we just did. 2x1, 2x2, 5, x minus y. And there you go. And you can see all these dynamics that we were talking about. So you can see that it asymptotes to one thing, and that we have this kind of nice kind of curvature that we expect as well. And for the first example, the line is for x minus 4, great. So here, on one hand, you can see this goes in, but also if you reverse these, if you think about the eigenvalues reversing, you can kind of see what we would expect to happen in the long term, going backwards. You can see how going backwards, all the arrows are slowly turning into the farther out eigenvalue. I wonder if it'll even, you can see it farther. Yeah. Okay, any questions before we get started back up again? So it's always worth, in my opinion, sorry, I lost the chat here. It's always worth, in my opinion, going through and using these computational tools, everything that you have available to kind of explore and understand the equations. But you know, you can get some kind of like vision of what the picture looks like a little bit, you know, like what it is that we're actually seeing. But then what the equations are really good for is when you want to then, so the picture, you know, so the computational side will give you a good sort of visualization of what you can expect. And of course, when you actually have solutions, I mean, we're doing all this eigenvalue equation stuff by hand. There's no reason that you should ever do this stuff by hand in the real world, right? Like, you should just fire up MATLAB or SymPy or whatever it is and just have somebody compute the eigenvalues and vectors for you. That's why we invented computers. But like a lot of applied math winds up being a bit of this interplay between the numerics and the equations, and you can just learn different things from them. So for instance, the fact that we can really classify this behavior and we can see exactly that those dynamics are coming from the eigenvalues and the eigenvectors, you can see from the equations. But getting an idea, sort of a picture of what the different kinds of solutions look like, the easiest way to do that, I mean, in my opinion, is to play around a little bit with the visualizations. It's one of the reasons that I really encourage you to do it in this class. All right. Are there any questions before we jump into the next batch of behaviors? So there are, I should of course also say, so the Bluffton one is one example. It's a web app that I think works pretty well. Of course, Mathematica also works well, as does Python, as does MATLAB. So it's kind of whatever you're comfortable with. Okay. So what about the following system? Consider the following system of differential equations. X prime equals y. Y prime equals minus x. Or x equals ax, or a equals 0, 1, 0. Okay, so let's give it a go. So the eigenvalues are going to be, well, we solve the determinant. A minus lambda I equals 0, or minus lambda 1 minus 1 minus lambda equals 0. So we have lambda squared plus 1 equals 0. Or lambda equals plus or minus the square root of -1. Okay. So this is a bit of a problem. And in order to solve this problem, we're going to need to try to make sense of complex numbers in a slightly different way of thinking about this. So, question, can we make sense of this? And the answer is going to be yes. Otherwise, I wouldn't be discussing it. But so the answer is going to be yes. And we actually get a whole bunch of quite interesting new behavior out of this. And new behavior. So, and never to spoil the punchline, does anyone know what the solution to this pair of equations is? It is something from basic calculus. if you sort of think about it correctly. You could ask yourself, well, what are a set of equations where if I take the derivative, one transforms into the other, and then the other transforms into the negative of the previous one? Okay, so let's recall a few facts about complex numbers. Let me just facts about complex numbers. Set of complex numbers is C, cosine plus I sine. Yes, that's exactly what we're going to end up getting. And in fact, if you look at the set of equations, it is cosine and sine that have that property that you take the derivative of one, it transforms into the other, and you take the derivative of the other, and it's negative the first. So I'm not going to go hugely into description of complex numbers. If you haven't taken a series complex analysis class, I highly recommend it. It's a fascinating subject. And complex numbers are just one of the greatest mathematical tools that we've developed in the past couple hundred years. It's like linear algebra. It just does things that you wouldn't expect to do because the theorems for complex numbers are so much stronger than for real numbers. So you can just get, if you can cast something in terms of the complex numbers, you can just get these really deep results very easily. Well, very easily. So what do we have here? Let's recall. So I is I squared is equal to -1, or I is sometimes formally called the square root of -1. Although we sort of don't, we have to pick a branch. We're not going to worry about that too much. So a number z in the complex numbers can be written as z equals a plus I b for a and b in the real numbers. And then multiplication and addition hold. Addition is, so a plus ib plus c plus id is a plus c plus I b plus d. Great. And so we've held the same form. This is the real part, and this is the purely imaginary part. Multiplication. So multiplication is just done by expanding. AC plus I AD plus I BC plus I squared BD, but by definition I squared is equal to -1. And so this is AC minus BD plus I AD plus BC. Great. Again, this is the real part, and this is the imaginary part. This is your crash course in complex numbers. So we also have the complex conjugate. So the complex conjugate is z bar, and it is going to be equal to a minus ib. Sorry, let me be a little bit more careful here, a little bit more precise. So if z equals a plus B, then Z bar equals A minus IB. And so importantly, Z times Z bar is equal to A squared minus B squared plus I, well, A B minus BA, 0. So this is A squared minus B squared, which is a real number. So if we multiply a complex number by its conjugate, then we'll always get a real number. And we can actually use this to define division if we want, right? So that means that actually that every complex number actually has an inverse, right? So it has a multiplicative inverse, something you can multiply it by to get 1, which is just the complex conjugate divided by, let me just write that. So Z inverse, or 1 over Z, is Z bar divided by Z times Z bar, right? This is by definition the thing that you can multiply Z by to get 1. Okay, any questions? Okay, so we can sort of, oh yeah, so note, a number is a real number if and only if. So a number, or a complex number, is real number is real if and only if, say a complex number, what do we want to call it? Let's do a Z. The Z bar is actually equal to Z, right? That seems like a very trivial statement, but we'll see in just a second that it's actually incredibly useful. Okay. So now to what we need to do. Well, okay, so in some sense, our situation hasn't actually changed, right? And our situation hasn't changed because we would like to be able to follow the same reasoning through that we did before. So now, we want to follow our reasoning from before. Oh, sorry. This is a real number if and only if this is true. And also, Z plus Z bar is a real number. And so I've given you guys the careful justifying proof. Let me give you the heuristic proof. Heuristic proof. Sorry, I always say heuristic solution. This isn't really proof. Heuristic solution. Z bar. It is. Thank you so much. Sorry. I made a huge mistake there. Thank you. That was a good catch. yes, that would be a disaster, because that would mean that the field of complex numbers actually contained a zero divisor, and so it's not a field, and a lot of mathematics would fall apart. So here's the heuristic solution to x prime equals ax. If this is helpful to you, then great. If not, then just remember the other one. So we want to do something stupid. We want to solve this by x of t equals e to the a t. Well, we need a little bit more than that, right? Because, of course, whatever this thing on the right-hand side is, it's probably a matrix. So e to the at times some v. Okay. We can do this, but how in God's name do we make sense of an exponential? So how do we understand e to the at? Well, so there's an important point that when we define the function e to the t, what do we actually mean? So like the natural thing to think of is that we mean, like, 2.71 blah 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 to the t, but that's actually not it, right? Because we would either need to take that number out to its entire real value, or you'd have to tell me how to compute that, right? So let's recall the definition of e to the t. E to the t. It is that e to the t is equal to 1 plus t plus t squared over 2 plus t to the 3 over 3 factorial, etc. That's the definition of e to the t as a function. And we can see that all of the nice properties that we would like fall from here, right? In fact, all of the nice differential properties that we get actually come out of this power series expansion. So we could define e to the at as 1 plus at plus a squared t squared over 2 plus at to the 3 over 3 factorial, etc. And lo and behold, this actually behaves exactly how we'd want it to. So note that d e to the at times dt is going to be what? It's going to be a plus a squared t plus a to the 3 t squared over 2 factorial, etc., which is exactly what we would want, a times e to the at. Okay, so this looks like a shockingly good candidate, actually, and we've tried to do something stupid, and we've actually turned out to do something that looks kind of good. There is one big problem with this, though, and that is that when we think about, like, t squared, t to the 3, etc., as long as t is less than 1, we know that this settles down, right? This actually has very, very predictable behavior. It's not clear if t, so the problem here, it is not clear if a to the n settles down in any sort of nice way, can be effectively computed. right? It's not like in the t case, you know, we're just multiplying a bunch of things by each other, right? A to the n is a series of multiplications and additions over and over and over and over and over. And this kind of thing has a tendency, I mean, as we're even seeing now, to be not very stable. And so it's very, very, very unclear if we can make any sense of this term for large n. Okay. But there is one thing we can do. We can make sense of it sense of this. So certainly, as far as like giving a formula or anything, if V is an eigenvalue of A, right? So then the formula suddenly becomes e to the x, e to the at, sorry, is an eigenvector. And what is this? Well, we do our power series expansion. 1 plus a t times v plus a squared t times v over 2, etc. And what do we get? We get v plus lambda t times v plus v times lambda squared times t squared. Sorry, there should be a square there, over 2. And all of a sudden, this looks like e to the lambda t times v. Great. And so this is an example of a solution. Okay, so I just wanted to show you that so we could see this other sort of view of how things happen. Now, we want to do this in the complex case. To do this, for lambda complex. Okay, but we need a real solution at the end. We need a real solution. And the answer is, in this Taylor series expansion, we can go through and we can do everything exactly as we would, is to use a complex eigenvector plus its complex conjugate. So this is where my barring things is going to be very difficult. Okay. And this should give us a real solution. Okay, any questions? So there's only one piece which we need to understand then, right? So one last piece. And that's the following. What is the complex exponential? Okay, so assume that we have a complex number. Then we're going to define e to the z is going to be defined in exactly the same way as we defined it for the matrix, right? We just go back to the power series definition, right? That is the definition of the exponential. So this is going to be 1. Oh, sorry, I want to actually be, before I do that, I'm going to write this as e to the a plus ib and pull off the real part. E to the ib. Okay, so then this is a, and let's put it through the power series expansion, remembering that I squared is equal to -1. So 1 plus ib plus ib squared over 2 plus ib cubed over 3 factorial, etc. What do we get? We get e to the a, 1 plus ib minus b squared over 2 factorial minus ib cubed over 3 factorial plus, etc. And then, what are we going to get? So if we rearrange these, and so that we have 2 power series, 1 minus b squared over 2 factorial plus this one being b to the 4th over 4 factorial plus I times b minus b cubed over 3 factorial plus, etc. And as Anjali said at the top of the hour, top of the section anyway, this is just the power series for sine. Sorry, for cosine. And this is the power series for sine. And so something amazing has happened, right? So we get that this is actually e to the a times cosine b plus I sine b. Oh, did I lose 9 in front of the b squared? I did not lose, so I didn't lose 9 in front of the b squared. Thank you. Yeah, I gotta brush over that. So because I squared is -1, right? And so instead of losing the I, what I've done is I've converted from I squared to -1 here. And so this is the, so there's this sort of amazing formula, and this is where it comes from, that e to the pi I plus 1 equals 0 comes directly from this fact. And this is probably, I mean, it's probably one of the most beautiful formulas in mathematics because it relates all of the fundamental mathematical constants in one go. But it's quite a nice little. There's no relation to all the great, yeah, I mean, all the fundamental constants. So you have Euler's constant pi, I, 1, and 0. And yeah, it doesn't really have anything to do with the rest of the class. It's just I can't pass this moment without pointing it out. It's a very beautiful thing about complex numbers. Okay. Great, so that's a complex exponent. So let's now go back to the example. Definitely is sort of weird, when you first learn sine and it's all about angles and construction and whatnot, and it turns out that it has this deep relationship to everything in the universe. Okay. Well, what did we have? So we had x equals y, we had y equals prime. So a equals 0, 1, minus 1, 0. And we showed that a minus lambda I implies, equals 0, further implies that lambda equals plus or minus I. Okay. So let's find the eigenvectors. So for lambda 1 equals so the way I'm going to do this is I'm going to say lambda equals I and lambda bar equals minus I. Let's do it out. So for lambda equals I, what do we have? So we've got A minus I times the identity matrix times V equals 0. And we can go through and we can write down the augmented system. So we have minus I, 1, minus 1, minus I. And okay, so we need to multiply the first line by something and add it to the second line. And you can see with a little bit of work, it is worth checking this, that if we multiply this by I and add it to this line, we get 0. Get our minus I, 1, 0, 0, 0, 0. And then let's actually write out the solution. So what does this imply? This implies that minus I times y1, let's see, I'm running out of constants. Let's see, let's say that our V, actually we can use V1 and V2 now, because we're going to use V and V bar. Let's just make it A1 and A2. Not be confusing. A1 plus A2 is equal to 0. So A2 equals I times A1, and V equals I. Okay, and in the interest of time, say it's worth checking that. Well, okay, actually, do it first. Just see first example. So what is A times V equal to? Good. Okay. Everything is working out. Okay. So I would say check for you guys that, but actually we don't even need to do this. sorry, I don't even need to do the next step. So now, A is a real matrix, right? So A times V bar is equal to A bar times V bar. Since barring numbers just factors through multiplication, we're not doing anything. Taking the complex conjugate, right? Is A times the complex conjugate. But on the right-hand side, of course, this has to be lambda bar times V bar. So if A is real, and we have a complex solution, and lambda has to be a non-real solution. Sorry, a non-real eigen value. Non-real eigenvalue with eigenvector v. Then lambda bar is also a solution. Sorry, lambda bar is also an eigenvalue with corresponding eigenvector v bar. So this also follows from the fact, so that of course, when we're factoring the determinant polynomial over the complex numbers, that has n distinct factors, right? Theorem. That has n factors for the complex numbers, and if that polynomial is real, then any of the complex numbers show up in conjugate pairs. But so this is great because it means that we can, if we do our first eigenvector carefully, so I may actually put this as a bit of an aside. So for lambda bar equals minus I, the corresponding eigenvector is 1 minus I. Okay, any questions? Because I'm doing a lot, especially if you haven't seen complex numbers before. I'm using things like complex conjugate very fluently, that if you haven't had a lot of experience with the complex numbers may be a little difficult. Okay. So now what does this mean? Well, it means that we can literally write down our solution, right? So what is x going to be? It's going to be e to the lambda t times v plus e to the lambda bar t times v bar and we want a C1 and C2, right? However, it needs to be the case that the right hand, okay. However, so the left-hand side the left-hand side is real. So the right-hand side has to be real as well. to be real. So in particular, we need that x equals, so we have our, let's do this heuristically, e to the a times, this has to be, and the thing in here has to be real. So if we have v plus v bar, it has to be c plus c bar. Okay. So this is real in R2. Why? Well, because it's something plus its complex conjugate. Each entry is of the form z plus c bar. Great. And that then is equal to this expression up here. So c lambda t v plus c bar e to the lambda bar t v bar. Okay. Any questions? All right. So I argue, oh, I should say, for c equals c1 plus I c2. So I argue that this is in fact real. And let's continue the example and see that it is. So this is x equals, well, c and c bar for the moment. So c e to the I t times, what did we have here? We had 1i c bar minus it minus I. So let's write down these solutions. So this is going to be x equals c1 plus I c2 times e to the it, if you remember, is cosine t plus I sine t times 1. So leave the 1 off. Plus c1 minus I c2 times cosine t, right? Cosine cosine symmetric with respect to 0, so cosine of minus t is cosine of t. Sine is anti-symmetric, so sine of minus t is minus sine of t. Is I sine t times 1. And let's just do the multiplication out, right? So, I mean, secretly, we know that it has to just be the real part of this, because that's what adding something to its complex conjugate does. It's just going to be 2 times the real part. But let's just check. So we're going to get c1 cosine t plus c1I sine t plus I, sorry, I c2 cosine t minus c2 sine t, okay, plus c1 cosine t minus I c1 sine t minus I, sorry, am I writing too much and trying to go too fast? I c2 cosine t minus c2 I sine t. Okay, so what cancels? So here this cancels with this, and this cancels with this. And what do we end up with? We end up with C1 cosine t, 2 times C1, minus 2C2. There shouldn't be an I here. Sine t. Okay. And for y, I'm just going to quote the result. I would say check this yourself, but we're going to get minus 2C1 sine t minus 2C2 cosine t. Okay, so something brilliant has happened here, right? In that we started off with basically exactly 3 kinds of behavior, right? We had expanding behavior, we had contracting behavior, but kind of everything went along these eigenvalues. And we could sort of go to asymptotic infinity, or we could go to 0. And that's sort of all that could happen. I mean, in some sense, everything that we were getting was just a 2-dimensional version of exactly the same 1-dimensional behavior that we'd seen before. But now all of a sudden, we see something really new. And the picture here is that the solution space is going to be given by closed circles. And with a little bit of work, we can figure out which direction they go. So for instance, if C2 equals 0, then it's going to be cosine minus sine. Somebody can probably get this faster than I can. But so an example trajectory is going to be C1 equals 1/2, C2 equals 0, and we're going to get xy equals cosine minus sine of t, so we're going around clockwise. So we have new when lambda 1 equals, is lambda 2 bar is purely imaginary. Say that would be that lambda 1 is in I times r. Oh, where is the y? Oh, so this was, sorry, yeah, so this, if you remember the way that I defined this originally, I defined it for x, y. And so in this case, yeah, so this is, I'm being ambiguous between if I give x a vector. Yeah, no worries. I'm being ambiguous in my notation between giving x a vector and saying that now is the vector xy. It's kind of standard, but it's a little ambiguous. Any other questions? Okay. So when this, the solutions are closed orbits. Okay. And in this case, 0, 0 is called center. All right, so let's look at another example. So what else can happen? So, okay, so this is amazing. So we go up one dimension and all of a sudden a completely new family of behavior comes out. But the kind of cool thing is that it doesn't, you might sort of think like, okay, well then this is, what even can we say? But because we know quite a lot about the eigenvalues and the eigenvectors of matrices, we actually also sort of know that, well, all the solutions are either going to be real or they're going to come in complex conjugate pairs. So as long as we can understand the behavior of two-dimensional systems with complex eigenvalues, that will sort of tell us everything. And then, in fact, the matrix really should be able to break up into an eigendecomposition where either everything is real or it's complex conjugate pairs. So look at a final example. So non-imaginary orbits. So truly complex eigenvalues. So we've looked at the case of imaginary eigenvalues. They're going to close up. Let's look at x prime equals 3x minus 2y and y prime equals 4x plus y. Okay. So let's just do the computation really fast. So if we have the determinant of a minus lambda I, this is going to be 3 minus lambda, 1 minus lambda plus 8. Which is going to be, there's a couple of different ways to figure this out. So what are we going to get? Lambda squared minus 4 a little confused. I'm not sure I've done this correctly. I'm sorry, I'm running out of time, and so that is stressing me out. Well, okay. So minus 4 plus or minus the square root, so 16 minus 4 times 11 all over 2. And this should wind up giving us then okay. Sorry, I apologize. I think that my example here, as I've written it, is not the correct eigenvalues. unless I've made some kind of terrible mistake. Just check something really fast. Yeah, so okay. Let's go with a slightly different example. I apologize. Okay, so let's go with 2x plus 4y minus x 2y. Should work out slightly better here. So we should get 2 minus lambda plus 4, or lambda squared minus 4 lambda plus 8. That should wind up with minus 4 plus or minus, 4 plus or minus square root of 16 plus minus 4ac over 2a over 2, which is 2 plus or minus I times 2. Great. Okay. Sorry, I just wanted to actually do that part of the computation so we can make sure that we know it. So, okay. So we can basically now, so in the interest of time, I'm just going to write down the solution form. I want to discuss the behavior here. So what is this going to be? So this is going to be c times e to the 2 plus 2 times t times v1, sorry, times v, I'm going to leave the hat off, times v plus the complex conjugate, so c bar, e to the 2 minus 2 times t times the complex conjugate. And so if you notice, we can factor an e out of this whole thing. So we're going to get e squared times c times the complex exponential, so sum of sines and cosines. So 2it times v plus c bar e to the minus 2it v bar. And so this, and I'll just state it, but I mean, okay, it's not hard to see. So the only functional dependence that this has on t, so this depends on t only through sine and cosine. sine of t, well, sine of 2t, and cosine of 2t. Right? C and V are constants. Oh, I apologize. There should be a t here. So in particular, what this is going to look like. So these solutions look like sums of sines and cosines. So that means that we are going around in a circle. Product of a cyclic piece, I should say. And a dilation factor. E to the 2t. And so the picture that we can draw of these solutions, right, is that we have x, we have y. Figuring out which direction that they go around is a little bit complicated, but let's. And you have basically, so you have things going around cyclically, and then you're spiraling outwards with. So you're going, sorry, so you're going around cyclically, and then you're spiraling outwards because we're dilating the entire function by e to the 2t. So since 2 is greater than 0, e to the 2t expands the orbit. As t goes to infinity. And we call this an unstable focus. Okay, any questions? And like, we can write down an exact equation for this. It's a little bit like, so you just have to multiply a bunch of sines and cosines together or use some factors or some properties from complex analysis to get them. But it will just be some sum of sines and cosines times this e to the 2t term. And so you'll be going around in a circle and you'll be going outwards. And so, okay, so if we have an unstable focus, what is going to be the other possibility here? Maybe, yeah. So the final basic behavior, actually, let me see what the criteria is. So for an eigenvalue lambda equal to a plus ib, if a is greater than 0, then the origin is an unstable focus. Okay, so what's going to happen if A is less than 0? Well, in this case, you can basically imagine what's going to happen. So then we'll have, so for example, what if lambda equals -2 plus I2 and lambda bar equals -2 minus I times 2? So then we're going to get something very similar, right? Then we're going to get that x equals e to the -2t times c e to the I2 v plus c bar t bar. And so we're going to have a spiral that's contracting. So roughly we're going to have something that looks like. And this is a stable Okay, any questions? Just as a quick note, whether it's clockwise or counterclockwise is going to depend on other stuff. I mean, for us, that's just going to be something that we can check. So, yeah. Okay. So I want to finish this off by saying just something about what we can say all together. And I might repeat this next time. So what have we talked about today? All together. We've seen quite about 5 different kinds of behavior. And these are summarized often in what's called the trace determinant plane. Here can be summarized in the trace determinant plane. And here's the basic idea, right? Is that given a 2x2 matrix, or 2x2, then the determinant of A minus lambda times I is written lambda squared minus lambda A, B, C, D. Write it out is A plus D plus AD minus CB. And this exactly is lambda squared minus lambda times the trace of A plus the determinant of A. So let's let the trace of A equal T and the determinant of A equal D. Then we can solve this as so 1/2. What did I write? Sorry. So this is 1/2 T plus or minus the square root of T squared minus 4D, where we sometimes call this delta. Okay, so this is our general solution. And what we can do now is we can draw the phase space. Okay, so if we have the trace and we have the determinant, then the line delta equals T squared minus 4D equals 0. This is what's going to separate our complex solutions from our non-complex solutions, right? And the determinant itself, so if the determinant is positive and complex, then what we're going to get is, so these are our unstable focuses. And these are our stable focuses. So these are going to be our, look like this. And these are going to be our stable focuses. So if we're above the T squared minus 4D equals 0 line, then we're in the complex, then our eigenvalues are complex, we're going to be stable or unstable. If we're right on the boundary, of course, then they're going to be closed. If we're below this line, then we're going to have stable and unstable nodes. So we're going to stable focus. Stable nodes. Unstable nodes. And then finally, for everything below, semi-stable. So if the trace is less than 0, we're going to be in the semi-stable world. So these are going to be our stable things, and then our semi-stable things down here. And so this is kind of the sort of one sentence summarized picture of all of the information that we've covered today. So we have our complex eigenvalues, complex Lags. Down here we have real lags. And these separate all of our behavior basically entirely, so all the behavior is determined entirely by the trace in the determinant. And the useful thing about this phase-based picture, not only is this going to give us kind of an index or guide to the different kinds of behavior, it means that as soon as we're doing something slightly more complicated, right, and we're starting to bring in things like parameters, so instead of just solving a single differential equation, or a single system of differential equations, we're solving some parameter-dependent family of differential equations, we just need to ask ourselves how the eigenvalues move around, or sorry, how the trace and the determinant move around this plane, and that will exactly classify the behavior for us based on those parameters. So I'll go over this again briefly on Wednesday, and then we'll actually start using this to look at some examples. So on Wednesday, we should be on schedule to discuss pharmacokinetic models and epidemic models, so the SIR model. And then we'll do a little bit of a lab. We'll finish with a bit of a lab talking about how to solve systems of differential equations with Python. I will post that lab today. And if you would like, you are free to take a look at it. It will be a similar kind of homework to last time. But we won't actually go over it and formally assign it until Wednesday. Or I guess it's formally assigned today, but we won't go over the lab part until Wednesday. But there are 3 problems on there which are related to the material today. Okay, any questions?
Professor, I have a question about the notes.
Mm-hmm.
On the second last question, it's like x prime equal to y and y prime equal to negative x. That question on your notes, I have like one thing not clear. Can you just like go back to that page if possible?
Is this, sorry, which part of the notes?
It's like x prime equal to y and y prime equal to negative x. That example.
Yes. Mm-hmm.
Yeah, and can I go down a little bit? Sorry about that.
Yeah, no worries.
Yeah, and here, yeah, I see. It says not like the A and V bar, like that equation. How can you get the last part, like get the lambda bar and V bar?
Yes. So the reason is, sorry, this is one of those, I should probably write this way. So then this here is lambda V bar by the eigenvalue equation. And this is
Okay.
lambda bar, V bar. Yeah, I jumped from one side of the equality, the string of equalities to the other. Yeah, definitely.
Okay, thank you.
Yep. Any other questions? All right, fabulous. Well, if you do have questions, please let me know. And yeah, I will talk to you, or I'll see you guys on Wednesday. And have a fabulous evening, or afternoon, or morning, depending on where you are. trend that we've been seeing, and the other trend we've been seeing that is actually kind of interesting, I don't have anything to say about it. The first people to put material online were T, right? Maybe somebody else may have been before them, but they were very early on. And it is an interesting example. Oh, so here.